So chapter 7 continues to build on our understanding of chemistry. We've gone through nomenclature, we've gone through writing balanced chemical equations, and now we're going to talk about different kinds of chemical equations. So we're going to talk about different reactions, and all of the reactions are going to happen in aqueous solutions. So we know that an aqueous solution, we would write with an AQ behind it, like all acids, and any solution is a homogeneous mixture. So your tea might be a homogeneous mixture. It's a solution. When we take a look at these, this is a bit of a throwback again to signs of a chemical reaction or signs of a chemical change. On a chemical equation level, if any of one of four things is going to happen or could happen, then a reaction will likely occur. And so this is what we're talking about. And some of these are familiar. So if a solid forms, if a precipitate forms, and oftentimes precipitate is long, so I'd go PPT for precipitate. That's one of the four forces that drive chemical reactions. The other one is bubbles. If there's a formation of a gas, then that's something you would notice. And those are things that you can see. And those are things that we talked about with signs of a chemical change or signs of a chemical reaction. The other ones are a little bit more invisible. And so we're going to talk about two other drivers in the formation of water as a product in a chemical equation. That's one of the drivers of chemical equations. And the last one is a transfer of electrons. And so this is the last kind that we're going to do. We're going to talk about oxidation reduction reactions or redox reactions, huge in the biological world. But basically these two things are not visible on a macroscopic level. You can't see those necessarily with your naked eye. And so those wouldn't have been things that you listed when we talked about signs of a chemical change or of a chemical reaction. So they're a little bit different. These four things are called the driving forces of a chemical reaction, and they do help us classify the different kinds of chemical reactions that exist. So the first part of this chapter, we're going to be considering two of them. So we're going to be talking about precipitation reactions and neutralization reactions or acid-base reactions. The precipitation reactions make a solid or a precipitate, and the acid-base reactions involve a water as a product. So water formation or water as a product. There's something worthwhile taking a look at. So in your formula pages, I have a summary. So chemical reactions is at the top of it. And this is a resource that you have access to that summarizes everything that we're talking about in all of chapter 7. So we're going to start off with precipitation reactions, so PPTs. And the driver here is a solid being formed, and acid-base reactions or neutralization reactions. And again, the driver here is that water is something that is formed. The next part of our notes says that both of these kinds of aqueous reactions are double displacement reactions. So let's go back to your notes and see what that means. So basically what it means is we have two ionic compounds and they basically swap partners. So the cation of one switches to the anion of the other and vice versa. So basically what we have here, and this is illustrated with X and Y and A and B, see this cation with the anion has now switched. So the X and the B are together and the A and the Y are together. And so this idea of doubly displacing the anions is why we call it a double displacement reaction. And all of the precipitation reactions we're going to talk about and all of the acid and base reactions that we're going to really focus on are these double displacement reactions. And we're going to do more of them as we go through. So again, these are aqueous solutions. And ionic compounds, like we're talking about with these, in a double displacement reaction, that could be a binary compound or it could be a polyatomic compound. It could also be an acid, right? If they dissolve, they dissociate. And we remember that dissolving doesn't necessarily mean dissociating. And so on the Moodle page, you'll remember that conductivity is linked to the fact if something dissociates, which means comes apart into the ion. So dissociation of ionic compounds would mean that the ions are free in solution. So the ions separate and move around independently in the solution. So as an example, barium nitrate is a solid white ionic compound with barium 2+ and nitrate ions. In this one, when it dissolves in water, it separates into its ions. And so when we see this, this is my barium nitrate being dissolved in water. So starting with this, you can see that in water it dissociates. Oops, dissociates into the barium 2+ and 2 of the nitrate ions. Remember that 2 down below is captured here. And in a sense, that balances this dissociation equation. So if we were to do the same, so K2CrO4, so that's potassium chromate, aqueous, will dissociate into 2 potassium ions in solution, so that's why the AQ is written after, and the chromate ion, 2+, that's a 4, sorry, not a 9, in solution. And really what we're showing here is not how things dissolve, but how they dissociate, because dissolving and dissociating are different. As a reminder, covalent compounds can dissolve like sugar, but they don't dissociate. And so in these ionic compounds, that's what we're talking about with these aqueous solutions and these double displacement reactions. So as we move on in the notes, the idea that we're talking about here are electrolytes. And so in these, dissolving does not necessarily mean dissociating. You can watch that little conductivity video. There's a picture down here. So this would be pure water or a covalently bonded solution. And then this would be an aqueous solution. So it might be salt water. That has free ions to conduct the electricity and the light bulb comes on. So just as a reminder, ionic compounds, when we think back to our nomenclature, we could have the type 1, metal and a nonmetal. We could technically have type 1 and type 2, right? Because the only difference between those are the multivalence metals. We could have polyatomics, because all polyatomics are going to be ionically bonded. And the third kind of ionic compound that we really have focused on would be acids. Bases factor into the polyatomics. Acids. So just as a reminder, and the key difference between covalent and ionic bonds or compounds, that's really what we're talking about. The manner to which things dissociate is basically identified by the strength of them as an electrolyte. And so if you think about an electrolyte, if you have Pedialyte, or if a kid gets dehydrated, you give them a Pedialyte, and that's basically a salt solution that they drink. Or if you think of Gatorade to increase hydration. So strong electrolytes, those are things that completely break up into ions and are good conductors of electricity. The other side of that continuum would be the non-electrolyte. So those would be covalently bonded compounds that might dissolve, but they don't dissociate. And in between, we have things that partially dissociate. So weak acids and bases and other substances that don't dissolve, that are ionic, but don't dissolve readily. They could be called weak electrolytes. There might be some conductivity, but not as much as a strong acid or a fully soluble ionic compound.